y equals 3. This is 1, so okay, that's the equation I get. This might be causing you to dig back into your mind from college algebra, but this is the graph of a hyperbola. Okay, it's not an ellipse because they're not the same sign. So I have two squared variables with different signs. So two squared variables with different signs, I get a hyperbola. And the shape of a hyperbola looks kind of like a parabola, but it doesn't have the exact same curvature. And it has two parts to it. So what you're seeing with that trace, so y equals 3, that would be one part of the hyperbola, this would be the other part of the hyperbola. And the 16 and the 25 does tell us something about the curve. If I make this the z-axis and that the x-axis, then there's a box that you can draw in between these two pieces, and the 16 tells me that one side of the box stops at 4, and the 25 tells me that the other side of the box stops at 5. So I know I drew this without thinking about that, but like this corner point of the box would be at 4 or 5, and then asymptotes to the curve go through the corners of the box. So the shape of the curve hugs those lines, and it's asymptotic to those lines. So if I draw, I apologize. I'm telling you, I have a clumsy day today. Okay, so the 4 and the 5, again, don't pick out the 4 and the 5 unless there's a 1 over here. That's consistent with all the shapes. If you have 1 over here, then you can interpret those numbers. But in the x direction, there's this box, and the extent in the x direction is 4 from where the center is. And then in the z direction, the extent of the box is 5 from where the center is. And then lines go through the corners, and those form asymptotes of the curve. So the curve is not a parabola because the parabola has a different curvature to it. This actually straightens out almost to lines as you get further out. Okay, so it's called a cone, but you do get some traces that are hyperbolas.